The transistor, first patented in 1925, it wasn't until 1947 that Bell Labs created a practically implemented device, for which its three inventors were granted a Nobel Prize in Physics in 1956. In the following year, Egyptian engineer Mohammed Atallah, also at Bell Labs, proposed a new method of semiconductor device fabrication, coating a silicon wafer with an insulating layer of silicon oxide so that electricity could reliably penetrate the conducting silicon below. This was the birth of the semiconductor industry as we know it today. 2 years later, Atallah developed the metal oxide semiconductor, or MOS, process, which he believed could be used to create a field effect transistor, or FET. The MOSFET has since become the most widely manufactured device in history. In 1963, the CMOS, or complementary MOS process, was invented at Fairchild Semiconductor, and in 1989 a team of researchers at Hitachi created the FIN field effect transistor, or FinFET, which is currently used in processors like the Ryzen 3000 series. It was precisely a former Fairchild Semiconductor employee, the Intel co-founder Gordon Moore, who predicted that the amount of transistors would double in integrated circuits every year. He revised that observation 10 years later to a cadence of every 2 years, and more recently, in 2015, Gordon Moore stated that he expected the so-called Moore's Law to be dead within a decade. Will transistors really stop scaling? What happens after 1 nanometer? And what materials could replace silicon in the microprocessors of the future? This video is sponsored by PCBWay. PCBWay offers quick turnaround PCB design with custom specs for low volume production or prototyping, as well as highly specialized precision PCBs and large-scale production. Get 10 free boards with your first order over at PCBWay.com, link in the description. The first thing we should address is whether Moore's Law is indeed dead. No, it is not. But is it slowing down, as many claim? Well, if we are talking strictly about density, then the answer is also no. Moore's Law will continue for several years. But if we talk about Moore's Law as a measurement for steady increased computing performance, as is commonly used today, then yes, it is indeed slowing down, but mostly because of bottlenecks in memory and overall costs in fabrication, and not necessarily due to transistor density increase. But general computer performance is a byproduct of Moore's Law, not the law itself, which is not even a law but an observation. It's important to remember that the rate of technological progress is controlled primarily from financial realities, and the financial state of the world doesn't stay constant. We've gone through periods of stability, of incredible prosperity, but also of wars, of financial crisis. There are bubbles and there are recessions. As a consequence, the rate of technological change varies over time. Just because there is a slowdown in technological advancements now doesn't mean that that will always be the case. Conversely, technological innovation typically leads to an increase in prosperity. In a recent presentation at the Hot Chips conference, AMD CEO Lisa Su talked about Moore's Law and particularly about how much it has historically dictated performance increases. In this slide from that presentation, we can see how Moore's Law is now at a 3-year cadence when it comes to transistor density. So that's the triangles plotted here. This other slide shows the microarchitecture techniques, with AMD claiming that process technology was responsible for only 40% of the performance speed up over the last 10 years. Even though I don't have the numbers that AMD used to produce this slide, I feel like this is wildly biased towards the chip design side of things. Traditionally, process technology accounts for closer to 90% of the pie when it comes to performance speed up over the years, and the last 10 years were no exception. So in my last video, I talked about how new advancements in packaging, in concert with data-centric architecture designs, will bring about massive improvements in performance in the next couple of years. In today's video, we will be focusing primarily on the other side of the coin, the process and the materials. We will look at the near future changes, but also into the somewhat distant future, including quantum computing. As it stands, this is the current roadmap from the main fabs. 7nm is out now, with Ryzen 3000 being the most prominent example as far as our niche is concerned, and it's still using good old FinFET transistors. 5nm is scheduled for production next year, both at TSMC and Samsung, using FinFET transistors but now with EUV lithography. Ryzen 4000 or Zen 3 will not be on this node, instead coming out on a refined version of 7nm. 3nm is expected to be in risk production in 2021, both at TSMC and Samsung. 3nm marks the introduction of a new type of transistor to replace FinFET. The gate-all-around FET has been in development for several decades and is now ready for large-scale production. This transistor goes by different names depending on who you ask, like nanowire or nanosheet transistor. Without going into too much detail, the idea here is to create a 3-layered channel completely surrounded by the metal gate in order to better control the leakage of electrons at such a small scale. The FinFETs we have today don't work properly at this scale, so this advancement in transistor design was necessary to keep us pushing forward. If you've been watching my videos for a while, you'll know that 7nm, 5nm, etc. are just marketing terms. These process names bear no connection to the actual physical size of transistors. But I'm sure you've wondered, how small can we make a transistor? From our current knowledge of physics, the only real limit is the size of a single atom. So if that's the only limitation, then there's probably at least another 20 to 30 years worth of scaling down. Then why are companies like Intel and AMD saying that Moore's Law is coming to an end? Well, that's the reality within the current context. So that's the current fabrication processes, the current materials, and more importantly, the current economics. I've talked in past videos about the S-curve. Moore's Law can also be modeled in a learning curve, except that the learning curve for Moore's Law is linear, provided the two original conditions are met. So Gordon Moore stated that every year the number of transistors would double and the cost of making chips would also go down. But remember, Moore adjusted the projection in 1975 to every 2 years instead of every year, and then in 1997 adjusted it down again to every 18 months. And like we saw earlier, today we are closer to 3 years. But here's the interesting thing. When it comes to transistors, Moore's Law existed long before Moore observed it. So if we look beyond MOSFETs and we separate the devices into several eras, let's call them, we have in 1941 to 1955 as the vacuum tube era, 1955 to 1966 as the discrete transistor era, and then 1966 till today as the integrated circuit era. And this is where Moore's Law takes place. After we chart the cost per transistor over time adjusted for inflation, guess what? The learning curve for the semiconductor industry has been linear since its inception, and it will continue to be that way. What is happening is people are stuck on this idea of the silicon transistor and its limitations. Imagine back in 1955 someone saying that the industry was going to stagnate because vacuum tubes had reached their limits. Sounds a bit short-sighted, doesn't it? And costs are influenced by the current financial and political climate. What AMD and Intel are referring to in these recent presentations is the point of diminishing returns in semiconductors as things stand. We hit a point of diminishing returns when increasing the investment makes the chips more expensive rather than cheaper. You can imagine this as us running out of cheap energy sources here on Earth and having to invest massive energy resources to go and get more energy from, say, mining asteroids in space. We would be using too much energy for very little energy in return. And if we have to go to asteroids that are too far away, we go from diminishing returns to negative returns, spending more energy getting there than we get in return from mining these hypothetical asteroids. So going down to 7nm has been an enormous expense just to get a small jump in performance. Going down to 5nm will be even more expensive, again with diminishing returns, and then down to 3nm and 1nm possibly becoming prohibitively expensive for most companies, given that the returns will be minimal if we continue to do things as we have been doing so far. So that sets the stage for what we will talk about next. What does the future hold? We went from vacuum tubes to discrete transistors to integrated circuits. What will the next era be like? TSMC suggests that being more creative with packaging, like using 3D stacking, will guarantee high returns on these growing investments, and that's where we left off in my last video. At Hot Chips, TSMC talked about its chip-on-wafer of substrate integration, or CoWoS. This thick boy is similar to what I discussed in my last video, although this is a much simpler chip than what I was proposing a couple of weeks ago. Going down to 5nm, this is what we will see: chiplets and 3D stacking with data-centric designs, as I discussed in that video. Somewhere between 5nm and 3nm, we will see something that I also discussed in the past, and that is massive amounts of on-chip memory, with 1 GB of cache starting to become the norm. So this is your level 4 cache. The most significant change here will be that HBM will now be stacked on top rather than next to the logic dies. This period will see a maturation of EUV, and a new generation for CMOS called High Numerical Aperture EUV, or NAUV, will be introduced in fabs. The gate-all-around transistor will also start to replace FinFETs in these next 5 years. So while these short-term changes might not seem too drastic, things will get very interesting very quickly after 3nm. 2025 will see the introduction of the 2.5nm node, which will bring innovations like the vertical gate-all-around transistor and up to 4 GB of on-chip L4 cache. That's right, 4 GB of cache on-chip, and that's thanks to advancements in interconnects and of course new memory. And here we will enter a stage where memory and logic will converge. There are several types of next-generation memory being worked on that are candidates for this integration. There's spin-torque RAM, phase change memory, resistive RAM, which has been the subject of a lot of attention recently, conductive bridge RAM, and ferroelectric RAM. Some of these, like spin-torque, are already being used in products today, and they will become more prevalent as we combine logic and memory. There are of course more exotic types of memory, like DNA-based memory, but that will probably have applications in massive storage rather than on-chip memory. It's too early to say which of these will win out, but my guess would be that MRAM, or memristor RAM, will be the one to bridge on-chip SRAM and logic. Sometime between 2026 and 2030, we will transition from the 2.5nm node to the 2nm node and then 1.5nm node. And I expect that carbon nanotubes will be used to make transistors on these nodes. In 2028, we will see mobile CPUs reach their frequency wall at around 4 GHz, after which point they will begin to regress as mobile CPUs increase core counts. For reference, the A12 in Apple's current phones has a max frequency of 2.5 GHz, so we will see a gradual increase in the next 10 years to around double the frequency on today's mobile chips. During this period, we will probably see the gate-all-around, or nanosheet transistor design, reach its limits, so we will see the start of stacking nanosheets and move to the 3D stacked nanosheet transistor. The tentative name for this transistor right now is CFAT. By 2030, we will finally reach the 1nm node. Again, this is just a marketing term. Here, carbon nanotubes will be prevalent in 3D form, and photonics will possibly replace copper wires. Before we look at what comes after 2030, let's have a quick look at some of the materials and advancements that will get us this continued Moore's law scaling in the period we just looked at. The carbon nanotube transistor was first demonstrated in 1998. In simple terms, carbon nanotubes are a 1D layer of graphene that's rolled into a tube. The idea here is to change the channel in MOSFETs to one of these tubes, at least for the first implementations, or an array of these tubes, to better control the flow of electrons. So in practical terms, a carbon nanotube transistor can reliably switch using much less power than than a silicon-based device, so this will result in much lower power consumption in your Ryzen 6000 or 7000 series processors compared to the silicon-based FinFET transistors we have today. But to be clear, silicon will still be used alongside carbon nanotubes for a long while, probably as a base layer. We will likely eventually see a transistor made with no silicon using only carbon nanotubes, but it's likely that silicon will stay around for several decades still in one form or another. Alongside silicon-based semiconductors, we are seeing the emergence of compound semiconductors using gallium and other elements like nitrogen to form gallium nitride. The 5G phones that you will be buying in the next couple of years will already feature compound semiconductors, and these will continue maturing in the next 10 years. It's possible that modifying the gate with ferroelectric properties brings about a negative capacitance transistor. Global foundries have been experimenting with ferroelectric on their 14nm process, but so far the devices have been unreliable. In addition to gallium nitride, there's also work being done with other 3Vs, namely gallium arsenide. These have so far been shown to be pretty good for things like RF power amplifiers, but not so much as candidates for the Xbox 3 or PlayStation 6 chips. Now back to our roadmap, and going beyond 2030, we'll first look at photonics. In simple terms, photonics aims to use light as a medium for switching in transistors, instead of using electrons like we have been doing forever now. The problem with photonics so far has been with the practical implementation. It's just too expensive and impractical to build a full photonics system right now. So at least in the short term, the most likely application for photonics is related to wiring. You see, copper wires don't scale with resolution, meaning that when we go down to 5nm, 3nm, 1nm and beyond, copper wires will have the same characteristics as they have today. They won't be any faster or use less energy. Photonics is one of the few candidates for future architectures that can solve this energy-related problem. Also, at a recent exhibition here in Europe, I found this really interesting discovery of luminescence in graphene. So it turns out that you can use a laser to open up a band gap in graphene, which results in light emission in the same spectrum as the sun. Well, if we're going to use graphene to build transistors anyway, and if they have luminescence when excited by a laser, why not combine lasers and graphene to create a photonic system? The transistor laser is actually something that is being researched and developed. This is in the same area as photonics, with the difference being that the photon to electron conversion can happen within the laser. And of course the advantages here are that light travels much faster than electrons, which means we could see speedups of hundreds of times compared to our current computers. The more likely scenario though, like I said, is that photonics in one form or another only gets used to replace copper wires. You will often hear very smart people in the semiconductor industry say that quantum computing will never be a real thing. These people either have a bias or just haven't looked at the history of this industry. IBM, Intel, and Google, and a few others like Rigetti, are in an arms race to create quantum computers that take processing far beyond traditional binary silicon-based systems. The reason so many are skeptical is that so far, quantum hasn't been demonstrated to be better than a conventional semiconductor processor at, well, anything. So you could say that quantum computing right now is not even on the same level of progress as ENIAC, the massive vacuum tube computer, was in the 1940s when it was first introduced. But there are enough similarities for people to get excited about quantum. My personal opinion is that once fully realized, quantum computing will be the single biggest advancement in human history. Now, any attempt to explain the scale of data that quantum quantum computing can compute will always fail to demonstrate how absolutely massive it is. But here's an example. Let's say you want to take coffee to the next level and make the best coffee that has ever been made. You can either go through millions of permutations in a test tube to test every possible molecular permutation, which would take you several lifetimes, or you can model the molecule of caffeine in a computer exactly as it exists in nature, so that a computer can run simulations to figure out what the best permutation is. How much information would that take? Can you guess? For an accurate model of caffeine, it's roughly 10 to the 48 bits of information, so that's 1 with 48 zeros. That's a big number, right? How big? The number of atoms in the Earth is estimated to be 10 to the 49th to 10 to the 50th. So the number of bits, so that's zeros and ones, just to represent our caffeine molecule in a single instant is roughly 10% of the number of atoms in our planet. Well, if you are drinking a coffee while you are watching this video, nature is modeling trillions of these molecules in that cup of coffee right now. The information is all there, being processed by nature without much effort. So when we talk about quantum computing, we have to let go of most of what we know about computing today. And that's why most people fail to understand quantum, and why there is so much skepticism. The problem with bits-based computers like the one you are using to watch this video is that they are inherently built to deal with relatively small amounts of data. When we're dealing with quantum mechanics and the laws that govern molecules and atoms and electrons, we need a machine that operates under the same laws. So there's nothing particularly magical about quantum computers versus classical computers. It's just a different framework. So you have to let go of the notion of logic gates and ands and ors, because those belong to a particular framework that doesn't scale to the amount of data that nature deals with. Qubits are artificial quantum particles that operate under the same laws of nature that govern quantum mechanics. So those are the tools for this additional framework that we have to help us solve these large-scale problems. So it's not so much that quantum computers will replace classical computers, they're a new tool for larger scale problems, especially ones with massive parallelism. So the two most important questions regarding quantum computing are not how we will get it working, because the math is already something we understand, but rather when will it become useful and what exactly will it enable. As far as when, most people estimate that it will take another 30 to 50 years for quantum computers to have the same sort of impact on society that classical computers have today. I think it's more like 15 to 20 years. You see, the rate at which qubits are increasing is not exponential, but double exponential. That means that quantum supremacy can be achieved within a few years, and after that we can have a transistor moment where quantum can have an enormous impact on our society, just like the transistor did. As far as you having your own personal quantum computer, I think that will certainly happen in our lifetime, although it's anyone's guess as to when exactly. As far as what sort of things quantum computers can enable, well, these range from simple things in the short term, like discovering new materials, to more complicated things like modeling molecules to cure diseases, and eventually to more exotic applications in a more distant future, like teleportation. Sounds crazy? Imagine telling the creators of ENIAC in the 1940s that within decades, thousands of people would be looking at a picture of them all at the same time in different parts of the globe, some even while taking a dump. They would have called you crazy too. If quantum computing makes your head hurt, what about thinking of what comes after that? To finish our journey, at least for now, I'll ask you to think about your favorite song. When you think of the chorus section in that song, you don't have to sing the whole song to remember it. The chorus just comes to you and you start singing it in your head, or an approximation of it. How did that process happen? As far as we know, our brains don't catalog different parts of songs so that we can recall them. In fact, most of the things we recall aren't actually stored anywhere in our brains. We just formulate them as needed. How strange is that? We're used to information taking some amount of space or energy, be it bits in classical computers or qubits in quantum. But the brain, which is the most complex system that we know, doesn't actually operate this way. Neuromorphic computer architectures aim to replicate this by using hyperdimensional computing. So one of the fundamental principles here is while classical and quantum computers are programmed to do specific functions, brains, both human and that of animals, are flexible and adapt to what each situation and moment in time requires them to do. So it's possible that the traditional von Neumann computer architecture, so that's RAM, a processor, inputs and outputs, can be used to create a neuromorphic system, but it's more likely that a new paradigm will be required to build a brain-like computer. What will that be? No one knows at this point. Such a system will probably take decades to materialize. It's likely that some form of biotransistor will be required, and that a completely different type of architecture will need to be conceptualized. I'll leave a link in the description to a white paper that proposes such a neuromorphic system if you are interested in looking that far into the future. As a parting note, and looking only at the next decade, the biggest takeaways as far as the future of computing performance is concerned are that we've entered a stage of hybrid scaling in regards to Moore's law. It's not just an increase in density of transistors anymore, it's the packaging that will change, the architecture, the materials, and the transistors themselves. And no, Moore's law is not dead. In fact, while many, including Moore himself, predicted that Moore's law would end in this coming decade, the reality is that we're entering the most exciting period in computer history, and the best is yet to come. If you've enjoyed this video and want to help my channel survive the ad-apocalypse, join my Patreon and get exclusive access to the Cortex Discord server, where you can talk to me directly about these topics. You will also get access to exclusive videos and presentations on computer architecture, and you will be joining a community of like-minded individuals. If you can't contribute financially at this time, then please share this video on social media, as that really helps. Thanks for watching, and until the next one.